Hi, this is a quick review of everything you learned about inverse in Algebra 2. So let's start first with the notation. In the notation we use f to the negative 1 of x. Remember, function notation is f of x. Inverse function notation has that little negative 1 right there between the f and the x. And that's how we know it's inverse. Now, it's not at the end back here because that would be a whole different type of problem. You'd be looking at a reciprocal because anything to the negative 1 power would be 1 over x. So make sure you get that negative 1 in the right spot when you're using your notation. In Algebra 2 last year, you learned 4 different things about inverses. You learned that if you're working with a table, you can switch the x and the y coordinates and get an inverse table and then plot those points and graph. If you're working with a graph where you're graphing an equation, f of x, then when you graph the reflection on the same graph coordinate, you will see that f of x, if its inverse is f negative 1x, will reflect over the y equals x line. So if you're trying to prove something is an inverse through graphing, be sure and include that y equals x line on your graph. The third way you talked about inverses was through equations. So an equation situation, the domain and range trade places. Now if that's just a regular xy equation, that simply means that the x and the y trade places and then you solve for y, because whenever we graph we have to have a y equals equation. But if you're in an application, it really is just the domain and range trading places. So you have to think about how you're doing your inverse when you have equations. Is it an equation in an application, or is it just an xy equation that you're manipulating? And fourth, composition. So if we find the composition of x of g of x, and that equals x. Now remember, x is the variable that is in g and in f. So all the math of working this problem canceled everything out and just left the variable. And then when you do it the opposite way, g of f of x, then you're plugging f of x in. All the math is canceling out the g's and the f operational stuff, and all you're left is that common variable. And when that's the case in both compositions, we say we find the composition both ways, then we know that they're an inverse. So I'm going to take an example. I'm going to work through all 4 of these just so you have a little refresher. So the first one is table. So I'm going to use the equation f of x equals x cubed. So I make my table for my parent function table for x cubed because that was the cubic function that we studied. And then I switch the domain and range so the x's and the y's trade places. So you can see how the numbers just change from table to table. I can graph these points. I have my inverse function, which we should probably already know is the cubic function anyway from our study last year. All right, then the next thing is graphs. So if we graph the cubic function, which is what's graphed here, and we have the point we have the point negative 2, negative 8, negative 1, negative 1, 0, 0, 1, 1, 2, 8. And then we switch those x and y coordinates like we did in this table right here, and we graph that table, we get this curve that looks like that, which is the cube root curve. So this is the inverse, this is the original function, and you can see that y equals x line is right there, and you can see that it does in fact reflect over y equals x. And you can even test that with a point. On the regular cubic function, it's 2, 8. That's not 18, that's just my comma. Kind of looks like it's an 8 and a 1. But if I have the point 2,8, then down here I should have the point 8,2. So you can see that reflection happening over y equals x. If you're dealing with equations, you would take the equation, you would change the x and the y because we're trading the domain and range, and then we would solve again for y. And when we solve for y, we get the cubic function. So using our notation, f to the negative 1 of x equals the cubed root of x, and those are inverse functions. And finally, composition. So if we have f of x equals x cubed and g of x equals the third root of x, then we're going to do the composition both ways. So this time I'm going to take g of x and plug it into f. So I'm taking the cubed root of x and plugging it into f, which gives me this. And I have opposite operations because this is cube root, this is cubic. So you're left with what's underneath, which is the variable x. Then you do the composition in the opposite direction. So we have f of x that plugs into g, which means we're taking x cubed and plugging it into g, which means when we plug it in, we get the cubed root of x cubed. And so opposite operations cancel each other out. And you can see the composition this way was x, the composition was this way was x. So since they're both x, we know that f of x and g of x are inverses to each other. So those are the 4 different things you kind of studied on inverses last year. Okay, I'm going to touch base real quick again with the horizontal line test and one-to-one. So here's my cubic function. When I do the vertical line test, it passes the vertical line test, so the original is a function. When I do my horizontal line test, it passes the horizontal line test, so I know the inverse of f of x is going to be the function, which means it's one-to-one since it passed both tests, and that every x is paired with a unique y, and every y is paired with a unique x. All right, next example is quadratic. So f of x equals x squared, and you can see the U-shaped graph right there. So I did my vertical line test. It passes the vertical line test, which tells me the original f of x is a function. And then when I did my horizontal line test, you can see it fails it because it's touching that graph in 2 different places. So when it fails it, then that's telling me the inverse of f of x will not be a function. And the inverse will fail the vertical line test. So here is the inverse to this. Remember, we would trade our x and our y, so I got this, which means you learned conic sections toward the end of Algebra 2, which is this is a sideways parabola, so it looks like this when it's graphed. And you can see when I'm looking at this inverse and I draw my vertical line, it fails the vertical line test. So this is not a function. Okay, but we knew that from right here by using the horizontal line test. All right, and finally, I always get the question about domain restrictions and when do you know to do domain restrictions. So there's really mainly 2 parts that we use them in more than anything else. One, if the problem says find an inverse function and the original fails the horizontal line test. So in other words, here's that quadratic we did a minute ago, but this is a function and it says find an inverse function. But when we do the horizontal line test, we know that that is not a function, right? We just showed the sideways parabola that failed the vertical line test. Okay? So what we do then is we restrict it. So what I did is I brought this half of the graph and left it, and I'm not using this part of the graph. So this is the equation, and you do that by just saying, putting a semicolon or comma and saying, I just need the x's that are bigger than or equal to 0. So now just this part is my graph. I have these points right here, and I can look at just doing the inverse to that part. So remember the quadratic turned sideways had the other part of the graph down here. Because we restricted it here, we'll only have this half of the graph. When our domain and range trade places, we look at our new point, and we can see right here when we look at that point, we know it is the square root graph. And this new graph now will pass the vertical and the horizontal line test. So when it says find an inverse function, but the original fails the horizontal line test is one case. The other case is when the answer does not match the original graph. So this time I started with the square root graph, which is right here. It passes both the vertical and horizontal line test, and here's the points that I'm using. And we want to find its inverse, so I'm going to do the equation method where my x and my y trade places. I'm going to square both sides to get rid of the square root, and I get y equals x squared. So this is y equals x squared. It's a full u. And that full u graph does not match the half of the u that was here in the original problem. So in this case, we're going to restrict our answer to match what the original graph looks like. So I'm going to only use this half of the graph because I want the top half of this curve right here to match this part. And so I'm going to restrict it and do all of the x's greater than or equal to 0. And if you look at these points, these are the points 0, 0, 1, 1, 2, 4. These were the points 0, 0, 1, 1, 4, 2. So you can see that that domain and range are trading places in the tables as well. You could put this on a coordinate graph and this on a coordinate graph, and they would reflect over the y equals x line. So all of those things that we've been talking about. So this is a quick summary of all of the inverse information that you learned in Algebra 2, and I hope that was helpful. There's also a copy of these handwritten notes in Canvas as well. Thanks, guys. Bye.